It is our great honor to have invited Professor Jack Dongarra from the University of Tennessee for insightful sharing on the development and future of the high-performance computing. Professor Dongarra is also a distinguished fellow of PAIR. To begin with, may I invite Professor Qingyan CHEN, Director of the PolyU Academy for Interdisciplinary Research, to deliver a welcome remarks online. Professor CHEN, please.
Thank you very much, Etta. Good morning, ladies and gentlemen. This is Qingyan CHEN. I'm sorry I cannot be on site to welcome you because I have a duty trip outside of Hong Kong today, which was decided last year. But anyway, I'm very excited that we could hold this distinguished lecture for Professor Jack Dongarra. As Etta just mentioned, Professor Dongarra is a distinguished fellow of PAIR. We are very proud of him. And this distinguished lecture is co-organized by PAIR and the graduate school. This is the first time these two units hold this distinguished lecture together. PAIR, as you already see from the video, is a new organization within the PolyU, which was established about 2 years ago. And currently, we have 11 research institutes and 6 research centers focusing on 3 major areas, like smart cities, advanced technologies, and well-being and health. So we try to address the societal challenges. And today we have Professor Dongarra to deliver the lecture on the high-performance building. And personally, I benefit a lot from Professor Dongarra's research, although he didn't know that because I was using linear algebra GNU to solve Navier-Stokes equation for the air flow inside and around the buildings. So this is a very important area to make people feel comfortable, healthy, and safe. So this is somehow connected to Professor Dongarra's lecture. And unfortunately, I cannot be on site to greet him and listen to his lecture, but I'm sure his lecture will really inspire PAIR and other researchers to use his knowledge to address different societal problems. So again, I would like to use this opportunity to welcome Professor Jack Dongarra, and now I will leave the time for Etta to carry on. Thank you.
Next, may I invite Professor Jiannong, Director of Graduate School, to come on stage to introduce our distinguished speaker today. Thank you.
Good morning, everyone. So welcome to this distinguished talk by Professor Jack Dongarra. And Professor Dongarra visited us about 4 years ago, 2019. And he also gave a talk on the high-performance computing. So it's our great honor to have Professor Dongarra back today and talking about overview of the high-performance computing and the future requirements. I mean, everyone knows now computer architecture has advanced a lot, and due to recent years in AI and then other kind of advanced computations. And so allow me to briefly introduce Professor Dongarra. He hosts appointments at the Oak Ridge National Laboratory in the United States, and also the University of Tennessee, and where he founded the Innovative Computing Laboratory. And Professor Dongarra actually is a pioneer in high-performance computing, and for his contributions, he received many awards, including 2019, he received ACM Simon Computational Science and Engineering Prize. 2020, he received IEEE Computer Science Computer Society Computer Pioneer Award. And more recently, he received the 2021 ACM AM Turing Award. And everyone knows Turing Award is just like Nobel Prize in computer science. And the citation for his contributions in the Turing Award is his leadership and the contributions to high performance computing, mostly in the numerical algorithms, mathematics, algorithm for linear algebra operations, and not only algorithms, and also he leads the development of computer software, programming packages, libraries used actually on different kinds of computers. And also he made contributions to the development of computer architectures. I think another one is very well known is he initiated this called Top 500 Supercomputer list. And actually everyone can use this to assess the development and advances in the supercomputing technologies around the world. That list probably was set up 30 years ago and still going on. So if you want to find out which lab, which country actually leads the development of a supercomputer, you can search the top 500 list. So without further ado, let's welcome Professor Dongarra to give us a talk on the high performance computing.
Well, thank you for that very kind introduction. It's a pleasure to be here with you today for this paired distinguished lecture series. It's nice to be back in Hong Kong. As was said, I was here about 4 years ago, and a lot has happened in that time. I'm going to be talking about high performance computing and look at where we are today with the field. So, there's this changing world that we have. Computers pervade all aspects of society. It has impacts on our socialization and communication. E-commerce and business are tremendously affected, as well as research and development. And we have a number of companies that are really doing, exceptional things. Companies like Apple, Samsung, Google, and Huawei really dominate the world of smartphones. And the interesting thing is that they are not using commodity processors. They're designing their own silicon. They're designing their own processors to effectively carry out the missions that they have. My laptop here is a device which is incredible. It has an M2 processor in it, and that processor has something on the order of 20 billion transistors in it. Incredible, incredible device. It has 8 cores. It has 10 cores devoted for graphical processing, and it does up to 15 trillion operations per second. So just an incredible device. I use it mainly to read email and also give talks, but it's really quite a powerful system on its own. And we have companies like Google, Amazon, Facebook, Apple, which really dominate the stock market. Each of those companies have capitalization. Their worth is over $1 trillion. And companies like Baidu, Alibaba, and Tencent are not far behind. And again, they're all designing their own silicon, their own their own hardware to satisfy the needs of their applications. If we take a look at the market capitalization of these companies, again, they're over $1 trillion in terms, each one is over $1 trillion in terms of their capitalization. If we take a look at the more conventional computer companies, if we add up the capitalization for those companies, just add up the traditional companies, it comes to just $1 trillion. So you can see that these companies like Amazon, Google, Facebook, and Apple are such a powerful entity in terms of computing. There's one exception to that, and that's NVIDIA, which also has a market capitalization of $1 trillion. And NVIDIA, of course, is being used to drive artificial intelligence. And that's one of the reasons why it's so popular today. But that's an incredible story of those companies. And again, the cloud vendors, the hyperscalers, as they're called, are designing their own processors. So they are not relying on commodity processors to do their work. They're designing their own processors that fit into the needs that they have. And that's true of Alibaba with its CIPUs. It's true of Amazon with its Gravitons processors. It's true of Google with its TPUs, and Microsoft has its own processors that they've designed. So they have this tremendous ability with the wealth that they have to be in a position to design their own processors. And that's even true of car manufacturers. So companies like Tesla has designed their own processors to help with some of their AI needs on their cars. So high performance computing, on the other hand, the things that we use to do scientific computing is really a monoculture in terms of its processors. We have this list that was mentioned called the top 500. The top 500 is a ranking of the 500 fastest computers. It was started back in 1993, and that list comes out 2 times a year. So we update the list with new entries in June and in November. The list gets updated, and it basically tracks and follows trends that occur in high performance computing. When we started this list back in 1993, there were 65 machines that used Intel processors in them, 65 of the 500 machines. And the rest really had specialized processors coming from companies like IBM, Cray, SGI, Thinking Machines, NEC, Hitachi, and Fujitsu. So this is a list here of the 500 machines. You could see in blue, I've highlighted the machines that used Intel processors early on and also AMD processors. And then something happened around 2004 that changed this story rather dramatically. And what happened is that we had this attack of the killer micros. So we had microprocessors that have become much faster and more powerful. And those microprocessors, because they were a commodity, began to fuel high performance computing. And we saw that this incredible rise in terms of the number of high performance computers that used Intel and AMD processors. Both of them have the x86 instruction set. So supercomputing today is driven by Intel and AMD in terms of its their capacity. 97% of all of the high performance machines are using Intel x86 architecture, and many of them are using GPUs to accelerate the performance. So GPUs are graphical processing units, and those graphical processing units are being used to do numerical computations that can boost the performance much higher than what we see out of those commodity processors. But the message here is that the traditional scientific computing is being driven by commodity processors. We don't have the resources that those other companies have, that we can design our own chips, we can design our own silicon to meet the needs. And many of the companies that were originally designing machines for high performance computing have either gone out of business or have really stopped providing hardware for this industry. If we take a look at the cycle time of our processors, we can track that over a long period of time using this top 500 data. So here's the frequency, the rate in which processors issue instructions. We see that back when we started this list, we had something on the order of 100 megahertz was the cycle time. That's the rate at which instructions can be issued by the CPU. And over time that rose to a point where back in 2005, we had something on the order of 2 gigahertz was the cycle time. 2 to 3 gigahertz was the cycle time. And then it became flat. It became flat and didn't change, is not changing today. So what caused that? So think about the situation that we have with the cycle time. In the old days, back here, when I got a new computer, the cycle time increased. And that increase in the cycle time made my applications run faster. I didn't have to do anything. I just put them on the new computer with the faster cycle time, and my applications ran a lot faster. And I was a happy guy because I didn't have to exert any effort to get there. But something happened here which caused the cycle time to become frozen, so that as new processors come out, it has the same cycle time as the old processor. And now I have to do something. So what happened was something called the ending of Dennard scaling. So Robert Dennard is a scientist. He works at IBM Watson Research, and he wrote a paper back then which said, as the dimension of a device, the silicon CPU goes down, the dimensions goes down, so does the power consumption of that chip. And with that, we have smaller transistors that can run faster. And that gave us this increase in terms of the performance. But when we reached around 3 gigahertz in terms of the cycle time, and the dimensions became small enough, we ran into problems. And the problems that we had is that as the dielectrics became thinner on the chips itself, and they had shorter channels, they were more prone to leaking voltage, and that leaking voltage caused the chips to heat up. So we have a situation where if we try to have a higher frequency, we end up heating up the chip too much. So we're stuck at this point of 3 gigahertz. So the equations that sort of dictate what happens go something like this. The power is proportional to the voltage squared times the frequency. And the frequency and voltage have a relationship to each other. They're proportional to each other. So that says the power goes like the frequency cubed. So what does that mean? If I make a processor twice as fast, the power goes up by a factor of 8. So that causes the chip to get very hot in the situation. So today our chips are running at 100 watts. So think about 100 watts in the size of your fingernail. If you've ever touched a incandescent light bulb, which is 100 watts, it's very hot. So we can't get things much hotter inside of a desk side machine. So we end up freezing the cycle time at around 3 gigahertz to keep that power consumption under control, so to speak. So that was the issue with Dennard scaling. We saw that the performance of our cores that we have in our CPU, so our CPU is made up of multi-core today, many cores. Each of those cores, think of them as a processor. And we saw the performance go up slightly over time. So we had a situation where the performance is rising, but it's rising very slightly. And if we take a look at the performance, not of a core, but of a socket, we see that that change has been much more dramatic over time, has a different slope associated with it. And that's the result of using GPUs, using those graphical processing units in our sockets, that we're able to do much more in terms of the performance. So as the frequency has been fixed because of the end of Dennard scaling, we're able to ride some curve because of a change in the architecture. And the architecture change was the use of these GPUs, which provided more performance in a given socket itself. And today, the accelerators, the GPUs, is really dominated by NVIDIA. So this is a graph looking at the performance over time of the various accelerators and how it's affected the top 500 list. If we take a look at the June top 500 list, the total performance of all those 500 machines is 5.2 exaflops, and I'll describe what an exaflop is in a moment. The accelerated systems provide 3.4 exaflops. So those accelerators are providing a tremendous amount of computing power to the list itself. So it's really helping to boost it. But it's dominated by NVIDIA. So NVIDIA really is the model that's being used both for AI and also for scientific computing. The interconnects that we have on our computers are really commodity interconnects, and those interconnects are in the form of Ethernet or InfiniBand. So those are two common off-the-shelf interconnects. So we have a situation where we're using commodity processors off the shelf, together with commodity interconnects, together with commodity accelerators to build our supercomputers. And that has an impact on the overall situation. And of course, Linux is being used on all of the machines together. In the US, the Department of Energy is a big user of high performance computing, supercomputers. The Department of Energy does a lot of numerical simulations, and those simulations are carried out on those supercomputers. Today, science is being driven by simulation. And it's often said that the country that has the biggest supercomputers can do the best science. So this is an important aspect of carrying out science today. Exascale, the Department of Energy invested about $4 billion over the last 7 years to put together a program to address exascale computing. So the question is, what do we get for $4 billion? Well, one thing we get is 3 supercomputers. So each of these supercomputers costs $600 million. That's just for the hardware itself. So the supercomputer we have at Oak Ridge is called Frontier. It's up and running today. It's based on AMD processors with AMD GPUs. So it's a commodity processor plus a commodity GPU. And the second machine that's in line is a machine called Aurora, and that's going into Argonne National Lab outside of Chicago. It's a Department of Energy laboratory, and that's based on Intel processors together with Intel GPUs. So Intel makes GPUs as well, and they're being used in that machine. And the third machine is going into Lawrence Livermore National Lab, and that machine is not yet put together. It's an AMD-based machine. It'll have the next generation of AMD chips. In addition to those three machines, we're really focusing on 21 applications. And this is the whole point of the exascale computing project, is doing work on these 21 applications. So each of these applications has some impact on energy, and it's being funded out of the Department of Energy. And they're using simulation to drive these science areas forward, including wind energy, accelerators, material design, nuclear energy, photonics, QCD computations, astrophysics, and so on. In addition to those 21 applications, an investment is being made in terms of software that will help those applications be developed and run correctly on these exascale computers. So there's 84 software projects that are being funded out of this. This project started 7 years ago, and it's about to end. It'll end at the end of this month, in fact. And the unfortunate thing is there's no project that follows at this scale. So this project today is employing 800 people at various Department of Energy laboratories and universities around the country, and there's no follow-on project. So we have about 800 people, very talented people, who have been working to develop applications and software for these exascale computers, and they're going to be without a job in about 2 weeks. And no project is there really to absorb them or to build them back. So my guess is that many of these people will find their way into industry working for companies like Apple, Microsoft, Facebook, Google, and using their talents to effectively drive those companies. So today's high performance computing area for scientific computations looks like it's a highly parallel computer base. It uses distributed memory. In terms of using these machines, most of the applications are written in C++, maybe some in C, some in Fortran. They use MPI to pass messages around explicitly. MPI is the message passing interface. They use OpenMP to do the computations within a node where we have shared memory. The fastest computer is that computer at Oak Ridge called Frontier, and it's able to execute a peak performance of 2 exaflops. So an exaflop is 10 to the 18 operations per second, 10 to the 18. And I'll talk more about that in a moment. But this computer has 8.8 million cores in it, 8.8 million processors in it. It has 9,400 nodes. So if you're going to use this machine at scale, and many do, you have to be able to orchestrate that number of processors and that number of nodes on your system. Each node of this machine has one AMD chip, and that chip has a number of cores in it, and that chip communicates to 4 GPUs to offload the computations it's doing to accelerate the performance. And 98% of the performance of this machine comes from those GPUs. So if you're going to use this machine, you had better be using those GPUs to get performance. So we have computers which are heterogeneous. They use commodity processors plus commodity accelerators to do their job. And the thing to note is that communication is very expensive on these computers. So that's probably the most expensive thing, is passing messages around, communicating from one process to another, moving data from memory into the processor itself. That's a very expensive operation. And these machines are over-provisioned in some sense for doing floating point arithmetic. So they have excess capability that really is hard to tap into in terms of doing the computations, because we spend most of our time passing messages around, doing data communication. In the old days, when I would look at algorithms, 2 algorithms doing roughly the same thing, and I was going to decide which algorithm to use, I would make that decision based on how many operations, how many floating point operations an algorithm would do. But today, that model of doing work based on the number of floating point operations really isn't relevant, because the machines are really geared to doing communication as being the bottleneck. So communication is the thing that we should really look at in terms of the efficiency of the algorithms. The floating point capabilities have changed a little bit. We traditionally think of doing scientific computing using 64 bits of precision. So if we add or multiply numbers together, we're adding together 64-bit numbers, adding them together, multiplying them, and getting some results which are accurate up to that 64-bit limit. We do 32-bit arithmetic as well in some applications, but more recently, we see hardware supporting 16-bit floating point. And that 16-bit floating point is there not really for the scientific applications, but it's there for doing machine learning and AI computations, because they can get by with shorter precision. They don't need such large precision. And as a result, the hardware has been changed, modified, to support that 16-bit floating point operations. And some hardware is even there that supports 8-bit floating point operations, again, for doing machine learning. So the fastest computers today are an exaflop, so we need to understand what that is. One flop is an add or a multiply. And in the context that I'm talking about here, it's 64-bit operations that we have. So 64-bit operations for adding two numbers, that's one flop. 64-bit operation for multiplying two numbers together, getting a result 64 bits, that's one flop as well. So an add and a multiply together would give us two floating point operations if we carried it out. An exaflop is a billion floating point operations per second. That's a hard number to get my hands around, a billion. I gave this talk a few months ago, and there was a reporter in the audience, and the reporter came up to me afterwards and asked me about supercomputing and exascale, and I said a billion operations per second. He wrote an article. When I saw the article the next day in the paper, it said 2 billion. This is not 2 billion. This is a billion floating point operations per second. So incredible rates of execution. So if we had everybody on Earth do one operation per second, it would take 4 years to equal one exaflop, 10 to the 18 operations. So that's sort of the computing power. At the University of Tennessee, we have a football stadium. That football stadium is like a cathedral, to be honest. It's used maybe 6 times a year. It's used to play football, American football, and it has 100,000 seats. So if we think about taking that stadium and have everybody in the stadium use a laptop like mine and connect them together somehow to do a computation, that device, that stadium with 100,000 laptops connected together would only give us 50 petaflops of computing power. So 5 times 10 to the 16. So we're not yet at 10 to the 18. So how many stadiums do we need to get to an exaflop? Well, we need 20 stadiums. So we'd have to connect together 20 stadiums of people with laptops to equal what that one exascale computer can effectively do. Now, this is a silly kind of computation, but it just shows the power of our computations. I became an accidental benchmarker back in 1979. In 1979, I was involved in a project called LINPACK. LINPACK is a package of mathematical software for solving systems of linear equations. And the project was carried out by 4 people. So one of the guys is Jim Bunch. He worked at the University of California, San Diego. Pete Stewart, who was at University of Maryland. Cleve Moeller, who was at the University of New Mexico. And this is a 1979 version of me with a little bit more hair. This is my car with a LINPACK license plate from New Mexico, where I got my PhD. So this project was a fun project. We developed software. It had a big impact. And in the appendix of this user's guide, I put together a table. I put together a table of solving a system of linear equations. It was a matrix problem of size 100 using the LINPACK software. I timed the time it took to solve that problem, and I put together this table. So this is a table, if you will, of benchmarking those computers where the fastest computer at that time was a computer at the National Center for Atmospheric Research, NCAR. It was run on a Cray 1, and it achieved 14 megaflops. The handwritten scribble is my translation of the time to solution into a rate of execution for this problem. So that was the origin, I'll say, of this benchmarking. It listed 23 machines, and since then it's basically had a life of its own. I got together with a colleague from the University of Mannheim, Hans Moyer. Hans had a list of the fastest computers that were ranked by the theoretical peak performance. The theoretical peak performance is a calculation you could do with paper and pencil. You look at how many processors you have, what the cycle time is, what the number of operations you can do per cycle, and that gives you the theoretical peak. So he had a list of computers with theoretical peak. I had a list of computers running a benchmark, and Hans said, we should get together and make a list of the 500 fastest computers. So we did that, and that list is called the top 500. It solves this system of linear equations, AX equals B, where the matrix A is a dense matrix problem, and the ground rules say that you have to use Gaussian elimination with partial pivoting to solve that problem. And you have to do it using 64-bit floating point operations. So full precision has to be maintained throughout the computation using that very specific algorithm for solving that system of equations. So we started collecting that data, and that data is updated twice a year in the meeting that's held in November and also a meeting that's held in June. So the most recent results we have is from that meeting in November last month. So this is a sort of a snapshot, if you will, of supercomputing going back to 1993 until today. The red line is charting here the computer at position number 1. So the fastest computer today is at 1.19 exaflops, 1.19 times 10 to the 18 floating point operations that per second. That's the rate for solving that matrix problem, right? So that's the actual rate of execution. The guy at the bottom of the list that just made it on, number 500, is at 2 petaflops. So that sort of brackets, if you will, supercomputing. And you can see where things have been in the past. There's this sort of inflection point here that's happened. That inflection point, I think, is caused by Moore's law slowing down, Dennard scaling happening, and also maybe a downturn in the economy that people didn't invest in high performance computing. So a number of things were going on about that time. So back in 1993, the fastest computer was a machine at Los Alamos National Laboratory. It was a thinking machine. It had 1,000 processors in it. It was a specialized machine for doing scientific computations. And at Los Alamos, it was used for nuclear weapon design. That's what they do at Los Alamos National Laboratory. My laptop, this computer here, I can run the benchmark on it. And when I run the benchmark on it, I get 426 gigaflops. So this laptop would have been faster than that machine at Los Alamos that was used for the nuclear weapon computations back in 1993. It's a device I use mainly, again, for reading email and for giving presentations. It has a battery that lasts 12 hours. I use it on a plane. It's an incredible, incredible device. Major changes taking place. This is the list. This is the top 10 list of that top 500 collection. The way to read this is number 1 machine. It's at a Department of Energy laboratory at Oak Ridge National Lab. It's called Frontier. The computer is integrated by HPE. So HPE is a company that doesn't make chips. They do integration. They take chips from other companies like Intel or AMD. They put them together in a box and interconnect them and then sell them. So this machine here uses AMD chips. It uses a 64 core chip plus an accelerator that AMD makes. And that makes up a node. And that node is built up until we get to a very large number. So the benchmark was run on a machine that had 8,600,000 cores in it, and it reached this execution rate, 1.19 exaflops, and that represents 71% of the theoretical peak performance. So again, the theoretical peak performance is a paper and pencil calculation based on the cycle time and the number of processors that are in the machine. So it's achieving 71% of that theoretical mark that the machine has associated with it. And you could see that this machine under load running the benchmark consumes 22.7 megawatts of power. So what's a megawatt? So think about it this way. At my home in Oak Ridge, Tennessee, if I use a megawatt for 1 year at my home, I'm going to get a bill for $1 million. So that's the cost of electricity in Tennessee. I'm not sure what it is here in Hong Kong. It probably is higher than that. Now, I don't use a megawatt at home because I would get a bill for $1 million if I did, and I don't have that kind of equipment. But this computer is using that kind of power. So the cost just to turn this computer on is roughly $22 million just to turn it on. The computer, of course, costs $600 million, so maybe that isn't a large cost associated with it. And this last column here represents the efficiency. It's the gigaflops per watt. You want that number to be as high as possible. And if we scan down this list here, we see that the US has 6 machines in the top 10. Japan has 1, Finland has 1, Italy has 1, and Spain has 1. The previous list showed China having 2 machines on the list, on the top 10 list. But those machines have been overtaken by new machines that came on more recently. So they've moved down and are not represented in the top 10 list today. So this is that machine at Oak Ridge National Lab. It's a peak performance of 2 exaflops, 20 megawatts of power. It's based on AMD parts and AMD accelerators. It has 9,400 nodes in the machine and is up and running and being used to solve challenging scientific problems today. If we take a look at the peak performance in terms of 16-bit arithmetic, we see that it's capable of even faster execution. 11 exaflops is what it's capable of. And it's important to note that if you use this machine, you really have to be using the GPUs in order to extract that performance. So 99% of the performance is coming from those GPUs. If you didn't use the GPUs, you would be down to around 1% of the performance that you would actually be able to realize on this machine. So this is that list of the #1 machine again, going from 1993 until today. There's sort of a threshold that was reached of a teraflop, 10 to the 12 operations back in 1997 with the first machine to reach that. 11 years later, we got 3 orders of magnitude improvement in the performance of the computers with a machine at Los Alamos with 10 to the 15 or a petaflop of execution being reached. And 14 years later, we got to the point where we reached an exaflop. So it's taking longer to reach higher levels of performance. And I believe that'll continue in the future. So, and that's caused by a number of things happening. Moore's law slowing down. Moore's law has not ended, it's slowing down. Dennard scaling has ended, and that now impacts the performance. And the architectural changes we haven't seen a major architectural change since the GPUs were brought into the scene. And that'll probably has a major impact. If we look forward, extrapolating from this data and looking at where we're going in the next, say, few years, it says that it'll take 8 years to get roughly 1 order of magnitude improvement in the performance of our computers, unless some major architectural change doesn't come along and help us. So this is the list of the top 500 machines. There are 500 dots in this graph. This is the #1 machine. This is the #2 and the #3, and so on down the list until we get to the number 500 machine. So you see this long tail associated with this graph here. And maybe we shouldn't have had 500 machines on the list. Maybe we could have gotten away with a lot less. So this is the list of the top 50 machines. And maybe that would be more representative of scientific computing. Many of the machines on the top 500 list are not being used for scientific computation. And I think maybe the top 50 machines has a better representation. So if there was a do-over, maybe we should have called it the top 50 list. There's rumored to be 2 or 3 exascale computers in China, but China has slowed down the submission of its list to the top 500. In fact, there were no new machines added to the list in November. So why hasn't China been adding machines? Why are they not submitting numbers for their exascale computers? Well, I think it's because they're concerned about the US taking some action against China, which they already have, to prevent technology from flowing into China. So today, China cannot acquire some of the more sophisticated parts from Intel or the West. So they pivoted, China's pivoted, and they have developed their own processors, and their own processors are in these 2 or 3 exascale machines. The machine that's in Wuxi called the Sunway Tahu Lite is a machine that uses their own processor designed in China that is able to reach exaflop performance levels. And they also have a machine called the Tianhe 3, which is also an exascale machine that's based on an ARM processor, which was modified to use an accelerator that was developed by the Chinese people. When I ask about those processors and ask about where they were fabricated, so you design a chip and then you send it out for fabrication, so you can realize the chip in silicon. In the US, we have some places that do the fabrication in the US. Many of the chips, the high performance chips, are sent to Taiwan to do fabrication at TSMC. When I ask the Chinese people and push them on this issue about where were the chips fabricated, they say, well, maybe they were fabricated at TSMC, but they also say that Taiwan is part of China. So maybe they were done in China. So China's reduced the numbers. This is the list. If we take a look at the supercomputers in 2022, China had 162 of the 500 computers. The US had 125. Today, because China has stopped sending results in, we only see 104 computers that remain. Number of machines have fallen off the list because the list is always rising. And the US has 161. So it's unfortunate, I think, that the Chinese have decided to stop sending machines. It sort of alters the trends that we've been able to observe. And I hope that would change somewhere soon. China is also the producer of the most machines. So these graphs here look at computers in the country. This annotation down here says who makes the most machines. And we see that Lenovo has 168 machines that they've produced. Inspur has 42, Sugan has 23, NUDT, National University for Defense Technology, has 3, Huawei has 2 machines on the list. So around 250, half of the list is produced in China and sold worldwide. So Lenovo is a good example of that. Okay, we have this benchmark that's been around for a long time called the LINPACK benchmark. And that benchmark has a lot of positive features associated with it. It's easy to understand. It shows these trends, and we can implement it quite simply on the computers. But a lot has changed since that benchmark was put together in 1979. The arithmetic was very expensive back in 1979. It was the most expensive thing to do on a computer. Today, it's over-provisioned. It's not expensive. The most expensive thing is passing data around on these computers. So LINPACK doesn't really correlate with real applications that are run on these machines. Most of the applications do not do dense matrix computations, which LINPACK does. So if you design a computer that gets a good LINPACK number, you're going to be in a situation where it may not perform well on real applications. So today's applications really look like climate modeling, combustion, nuclear reactors, fusion, material design, and accelerators, and so on. Those problems arise, those problems have a common situation where they're basically based on 3-dimensional partial differential equations. So when you discretize those differential equations, you end up with a linear algebra problem again. And that linear algebra problem is not dense, it's sparse. And there are different methods that are used for dealing with the sparse matrix problem. And that's really what sits at the core of most applications today. So what we want to do is to have a benchmark which reflects that. So we have a new benchmark called HPCG. It does a conjugate gradients algorithm. That's an algorithm which is used to solve those sparse matrix problems. The matrix itself looks something like this. It has a lot of zeros in it, and it has this banded structure where the non-zeros exist. The matrix is very large. It's an iterative process. where we have to iterate over the matrix, doing a matrix vector operation. There's a preconditioner which is used to help accelerate the performance of the computation, and it produces quite distinctive results. So here's the top 10 from this HPCG benchmark. It sort of rearranges the order of the machines. The number 1 machine turns out to be this machine in Japan. So this is the LINPACK number that we got, HPL number that we got for these machines. And this is the number that we get using HPCG. So it's quite different in terms of the amount of rate of execution that we see. In fact, this last column reflects the percent of peak performance that we're getting out of these computers for this application, which is very, very much like many applications run on these supercomputers. So the machine in Japan, the Riken supercomputer, the Fugaku system, is getting 3% of the theoretical peak performance. And that machine at Oak Ridge, which was number 1, is getting less than 1% of the theoretical peak performance. So don't tell anybody that. This is sort of our dirty little secret in some sense, that our supercomputers are not very efficient for the problems that they're really solving. So think of it like this. If you were using, if you had a race car, and that race car was capable of going 200 miles per hour, and you were getting only 1% of that performance, you'd be going 2 kilometers per hour. So that's sort of a big change in how we perceive things. One of the more efficient machines on this list is a machine in Japan. It comes from NEC. NEC is a computer company which still makes vector computers, and they have very high bandwidth for moving data around. And the results of that is that they get on the order of 5.4% of their theoretical peak. So they're able to raise the theoretical peak, but it's still quite disappointing in terms of that. So recently we've seen AI and machine learning taking off. Machine learning has been around, AI has been around for a long time. So why has this happened today? So it's happened because we have a flood of data that can be used for the training of the machine learning models, right? Especially with the internet, where we can scoop up all the data and push them through the machine learning. So, and we have this increased computational power, which comes about by these GPUs. We have this growing progress that's been made in terms of the algorithms and theory behind machine learning. And we have this increasing support from industry, which is promoting the use of these machines. So that all combines. The machine learning is really based on small matrix multiply, dense matrix multiply computations. That's what's really fueling this. But they can get away with short precision. They can get away with 16-bit floating point arithmetic in those computations because they don't need very accurate results. And what we've seen is a number of companies start up that produce hardware which is addressing the machine learning aspects, the training aspects, perhaps, of this problem. So these companies all make hardware in this space. They're trying to address a problem. And it's a situation which is very similar to what we had back at the start of this century. We had a lot of companies beginning, showing up, producing parallel computers that were trying to fit into the space of scientific computing by doing parallel computing, something which was new at the time. And I see this as a similar situation. Many of those companies that were doing parallel computing back at the turn of the century are no longer in business. Some of them were absorbed by other companies, or they couldn't really sustain a market and they went out of business. I would suspect that many of these companies will fall to a similar fate of being absorbed or being put out of business. Floating point has been around for a long time. We have a IEEE standard for doing floating point arithmetic. A colleague of mine received the Turing Award. He was very instrumental in getting this standard adopted and in place. And today it forms the basis on which we do our scientific computations. So we have the ability to do 128-bit floating point, 64-bit is realized in hardware, as is 32-bit, and IEEE specifies a 16-bit precision floating point. The 16-bit that IEEE is targeted at has a very limited range. So the largest number that you can represent in that format is 65,000. So if you get a number larger than 65,000, it causes an overflow to occur. And that causes a lot of problems when using 16-bit computations, because it requires a lot of scaling to go on in the application to accommodate that. Google said, this is too important, we can't have the scaling, so they made up their own format called bfloat16, and bfloat16 devotes 8 bits for the exponent, which is the same as the 8 bits used in single precision, so they have the same dynamic range as single precision, and they give up the accuracy. They only have 7 bits to represent the accuracy. So that's what's done there. NVIDIA says, well, we can do better than that. They have hardware that supports 8-bit floating point arithmetic, and they have 2 flavors for it. I have yet to find applications in the scientific area that can benefit from 8-bit floating point, but I'm sure it can be used for machine learning applications. So there's the opportunity here to use mixed precision in our scientific computations. We want to use mixed precision because we want to really have the accuracy of 64-bit, but we don't want to pay the price of moving all that data around or the expense of doing the operations. So if we reduce the size of the data for part of the computation, we can minimize the amount of data traffic that we have and also get the benefit of that, of the operations being done at lower precision. So the idea here is to mix precision in our applications, exploit lower precision for as much as possible, use selectively higher precision to do the computation. And the hope here is that we can increase the accuracy using some mathematical techniques to promote the precision to get back to the point where we have maybe the full 64-bit accuracy. In linear algebra, there's an algorithm which does exactly that. It's an algorithm called iterative refinement. You basically can think of taking the matrix and doing a factorization of the matrix in short precision. That factorization consumes n-cubed operations for a dense matrix, and then do a solve process, which gives you an approximate solution, which is order order n squared operations, and then iterate on that until we get to a solution. So that's an algorithm that uses a technique which is really Newton's method. It starts with an approximation and then refines that approximation selectively using 64-bit until we get to the point of getting the full accuracy. And a lot of work has been done on this algorithm as well as other algorithms to try to exploit mixing the precision to get the advantages of that. In this particular case, this is what happens on an NVIDIA processor. This red chart here shows what happens, gives the execution rate over time for solving larger problems, and we see that it achieves a certain rate of execution. If we use that algorithm I just described, going to 32-bit arithmetic and then iterating the process to getting to a 64-bit accurate solution, we end up going twice as fast. And that twice as fast gives us the same accuracy as we did using the 64-bit operations. So we're able to accomplish exactly what we set out to do, getting the solution twice as fast with the same accuracy as if we had done the whole computation using this mixed precision approach. And if we go to 16-bit arithmetic, we can extend that even further to enhance the performance along the lines of getting even better. And if we use the special hardware on the NVIDIA card, we can even enhance that to a point where we go even faster. So it's a good story. We have a benchmark which looks at this, of course, 16-bit arithmetic, enhancing the precision using that iterative technique so that we get exactly the same solution as we would have had we done the computation in 64-bit accuracy. And the table looks something like this, with this being the original execution rate using 64-bit arithmetic. And then we see a speed up, in this case, a factor of 8 if we did the computation using this mixed precision, 16-bit to do most of the work, and then enhancing the accuracy through that iterative method. And that holds true for many of the machines on the list. We even reached 10 times faster for some of the examples here. So here's my last slide. The takeaway here is the hardware for high performance computing is constantly changing. We went from scalar computers to vector computers, which boosted the performance, to distributed computing using parallel processing, which boosted the performance again, to accelerated hardware through GPUs, which helped boost the performance again, and now maybe exploiting mixed precision to take advantage of some of the hardware that's there. We've seen 3 computer revolutions, high performance computing being one, deep learning being another. We haven't really talked about edge or AI-based computing in detail, but that's another revolution that's affecting things. We have this situation where the algorithms and software for high performance computing really follow the hardware. So think of it like this. You know, we specify a machine that we would like to purchase based on the amount of money that we have and the rate of execution we think about for the peak performance. And we give that to a manufacturer. The manufacturer goes away and bids a machine which cobbles together parts, which matches the price budget that we have and the performance we're looking for. And we select a machine from the list of machines that are proposed. And now we're faced with trying to use that machine to develop our algorithms, our applications, and our software that can effectively use the hardware that's been given to us. And that's a daunting challenge. It takes us about 3 to 4 years to really get our algorithms and applications running on these machines effectively. And at that point, a new machine is thrown over the fence, replacing the machine that we just purchased 4 years earlier with a new architecture, and we have to go through that process all over again. So that's something which leads us to a very frustrating, perhaps, situation. There was a paper published a few years ago in Science magazine called "There's Plenty of Room at the Top. What will drive computer performance after Moore's Law?" My colleague Charles Leiserson and a number of his friends put together the paper, and it's interesting reading. It talks about many of the things I've touched on here. It's a riff on Feynman's lecture that occurred back in '59, where he was talking about there's plenty of room at the bottom, talking about quantum computing, and talking about how to exploit those things to really build systems out of things at the bottom. So there is plenty of room at the top. We see only 3% of the theoretical peak performance being achieved for many applications, and we should work harder perhaps at devoting time to the algorithms and software. But the real situation here is that we need to be more involved in the architecture that's designed for high performance computing. We should get together with the hardware architects, together with the applications people and the software designers, so that we design a machine that can effectively be used by the community. So with that, I'll stop, and I'd be happy to answer any questions. And thank you so much for your attention.
So now actually we have this question and answer session. So all are welcome to ask questions to Professor Dongarra. Yes, Jiannong.
Dear Professor, thank you for your presentation. My question is, actually, I'm working on deep learning and artificial intelligence part, and I think the top supercomputers, they lead the development of deep learning. But some deep learning products, such as GPT, ChatGPT, those large language models, they are also limited to the top supercomputers. For example, if I'm a school lab, I can hardly develop such a large model. So there's another direction called local software. That means somebody who cares privacy and security would like to develop such deep learning models on their personal computers. So there are many efforts, some communities working on, such as the machine learning compilation, try to make the large language models influence on personal computers possible. So do you think this direction is a promising direction, such as the Mac OS, they have their M2 cores, and people say they can run machine learning applications. So do you think those local software or the local deep learning stuff will work in the future?
Well, so I think that's an interesting question. Of course, the situation is that in order to do the large language models and such as GPT-5, it has 1 trillion parameters that have to be used in the analysis. And, that's hard to do on my laptop, the trillion parameters. So, that really requires a supercomputer running for months to do the processing required on it. And I don't think we're going to be in a situation where we could possibly do it on our laptop. But I think that's a good area to research. How can we better optimize those algorithms so that we can use something less than months of computing time with trillions of parameters to be in a position to do that. And perhaps we don't need all of that power in our large language models. So we can get by with something else which is more specific. And maybe that specific thing could be used on a smaller device where it doesn't take as long. But we're just at the beginning. I'm stunned at what's happened in the past year. Remember, ChatGPT came out 1 year ago, and it's had a tremendous impact. And we're really learning, trying to learn quickly how we can effectively use that tool in our work. And it's had a tremendous impact, and I think it'll continue to. So I think it's a good time to invest in trying to understand how we can better do things. So I think that there's hope for the future. We're just at the beginning of this whole process, and we have many things to learn and many things to investigate to try to make it a better situation.
Other questions? Yeah, Yang Yu.
Thank you very much for the informative talk. I have a question is like this. Nowadays, we have more application that require the GPU to compute, to train the model. And some people just say that probably in near future, GPU and CPU will be integrated as the one, and probably the for non-human models will be changed. So my question is that, could you please share with us your vision on the future computer architect? Would the phenomenal model still be the best choice for us, or probably we may need a future computer architect? Thank you very much.
So what you're referring to is the fact that today's model for computing says we have a CPU and a GPU. And in order to use the GPU, we have to move data from the CPU side to the GPU side, and then tell the GPU to do something, to do a computation. And then when it's finished, collect the data and move it back to the CPU. So it's a very communication intensive operation. It's something that has to be programmed manually. It's an issue of devoting programming time to put together such algorithms, and that's very tedious. So the whole process is tedious. It takes a lot of time. In the future, we hope that the CPU and GPU, as you say, come together so that we have tighter coupling between them, and that's happening. So I mentioned one of the computers that's planned is a machine that's going into Lawrence Livermore National Lab called El Capitan that'll use AMD's newer chips. AMD's newer chips integrate the CPU and the GPU. So it's one chip, so much less, much easier to move information across that boundary and be able to do the computation. So things are moving in the right direction. Now, what's going to happen in the future? I don't know. I wish I had a crystal ball that would predict. But in the future, I think we're going to have computers which will assemble based on the needs of the applications. What does the application need in order to make it go forward? It may need some other kind of computing device, maybe a FPGA. So I can envision a machine which had this CPU, GPU, plus maybe an FPGA connected to it, and they could share information and communicate. Or maybe it's a neuromorphic computing, something like our brain reacts, and have that connected in there. Or maybe at some point in the far future, a quantum computer connected into this situation, or a photonic computer. We have computers that shine two light beams, which represent numbers, and when they interact, they multiply the numbers together. Something which is very fast. It operates at the speed of light, and maybe something like that could be designed. Those are all future things. They're not happening today. We're just experimenting with quantum computing, trying to understand what the real impact might be in the future. But they're great areas for research. And again, I think there'll have to be changes that take place in the architecture that will allow us to go forward and make a major step forward in terms of the performance that we see.
Okay, I think here we have some questions online. So the question from Hawa Kim, saying, asking, is there any good alternative to CUDA from NVIDIA that is a universal for all accelerators, window independent?
Right, so CUDA is the mechanism by which we execute stuff on the GPU today, NVIDIA's GPU. So CUDA, think of it as a supplement to your language. It's a set of routines that you call that do operations on the GPU. So again, there's this interplay between the CPU and the GPU. You have to write two programs, basically, one for the CPU and one for the GPU. And CUDA is the mechanism that executes things on the GPU. And CUDA is something that NVIDIA created. So we have many GPUs today. We have GPUs from AMD. We have GPUs from Intel. We have accelerators from other sources. China has their own accelerator that they've used on the Tianhe 3, which is not CUDA. And now the question is, what can we do to effectively drive things forward? I like to start from a standpoint of having portability. Portability would be nice. I want to be able to take my application from this machine to another machine and run it, where I don't have to make major changes to it. That's sort of the basis for things. Our computers go away after 3 or 4 years. We get a new computer. And now if we have to change everything to move to a new computer, which may not have the same kind of devices, GPUs from NVIDIA, we have to rewrite the program. That's one reason why we created something called MPI, the Message Passing Interface. We got the community together and created a standard for doing communication on our computers, wherein before it was the Wild West. Each manufacturer had their own way of doing it, and we couldn't port programs from one machine to another. So we need something like that, to be honest, to be in a situation where we can do that. We're in a situation where NVIDIA dominates the GPU, so they're not going to change. And we have to get in a situation where we're in a more cooperative vein, so we can effectively get a standard developed for it, or come up with a mechanism so that CUDA, if that is the standard, is represented on the other machines.
Okay, another question from online. I think this audience worked back in 1980s. He said that his career has been built upon LabPack and SkyLabPack to solve the X equals B. So technical question asked that now we have a SLAB working on AMD GPUs. So I also tried it on AMD CPU, but it does not perform as well as the SkyLabPack on CPUs. Is this consistent with your expectations?
So this user is a very informed user. So I mentioned a software package called LinPack. So LinPack was software that was developed in the 1970s. And that was replaced by something called LAPack. LAPack was a software package just at the turn of the century. We created it, and it was trying to address shared memory multi-core architectures. That was really the point of LAPack, and it replaced LinPack, the replacement of a software package. And then when parallel computing came, we redesigned the package to deal with parallel processing using MPI. And that package was called ScalaPack. So we've gone through evolutions of hardware from scalar machines, LinPack, to LAPack, where we have multi-core, to ScalaPack, where we have distributed memory. And today we have a package called Slate. Slate is a replacement for all of that stuff. And Slate is intended to operate in addition to those things on GPUs. So Slate is a software package that will allow the user should not worry about where they're running their machine. The underlying software will figure it out and do the right thing. So in the design of Slate, which is a new package, we have inefficiencies that are created because we haven't sorted everything out yet. We haven't understood really the space where that software should live. And this user here is sophisticated in that he's probably used Slate, so he understands that the performance is not as good as it has been on some of the other machines, but it also suggests that maybe he doesn't use GPUs. Slate is designed to effectively use GPUs, and we haven't tuned it for all the other architectures that we're dealing with, and that will come over time. So software is a is something which takes time to develop and implement. And of course, things change rapidly. So we have to be prepared to make those changes as we move forward.
Okay, thanks. So now from audience here and questions. Okay, yes, please.
The Dongarra from your overview of the computing power of the current supercomputer, and it was quite impressive as I'm not from a computer science background. So I have a more general question. So I was quite surprised that like the current software development, like as what you have mentioned, like really follows after the hardware development. But from what I have experienced, I'm not sure quite the current software can like utilize the computing power of our computer efficiently. For example, like no matter you're using different OS system like Windows or Mac OS, or even within the Mac OS system, after an upgrade, like from like older generation of OS system, some software already cannot be used like in the past generation. Like currently in the new update, you already cannot use the past program, which could be quite disappointing. So do you have any insights or comments like how the software can come together with the hardware development? Like I was so stunned by how strong the computers can calculate, but like I'm guessing the effectiveness of how the software can utilize the hardware, like any comments on how they can communicate like more effectively, like to push the efficiency or effectiveness of how we can use these computers?
Right. So you bring up a number of issues, of course, and they're hard to have simple answers to. As the computers change, as the operating system changes, the underlying software may have to change to accommodate that. And in certain cases, the underlying software needs to be replaced. It can't just be used on the new computer. It needs to be redone. You need to, in the case of my laptop here, occasionally, if I go from one version of a Mac to the newer version of a Mac, the chips are changed even from going from Intel to a ARM processor, and I have to replace the software on my machine. So I may have to repurchase software in order to do that if I bought the original software. And that I find that a little bit unfortunate. And we could have translators which may avoid that situation so that we can translate the old stuff that runs on the new machine without having to make any purchases, but it may run slow. So we may experience a slowdown in our performance as a result of that. And that's just the fact of life that we have to. So software is a hard thing to accomplish in a portable way, in a way that lets us transition. If it's done, if we're able to do it correctly, then we could get the benefits of the new machine without having to experience a lot of the problems, but we're not always capable of doing that. That presents us with the problems you're asking about.
Yeah, because not to mention about programming itself, like it already has a lot of languages, C++, Python. Like from my experience of using, like a taste of using machine learning, I tried to run the Python code on my Jupyter notebook with the Mac OS, but I was quite surprised that, oh, I cannot use it on a Windows computer because there's a computing, like a prompt already. So I was quite, oh, that's the case. So it was quite a surprise that how different system or how different language come together with different like effectiveness of communication of utilizing these.
It would be nice if we were able to have that portability, and in some cases we just it just doesn't work. We have to resort to either rewriting the software or purchasing, and that's an unfortunate situation.
Thank you for your answer.
Okay, short question from online. Is there a feature where we could see in Zeta Utaflop in the future?
So we're at exascale today. Exascale is 10 to the 18. So what's next? 3 orders of magnitude is zetascale. So 10 to the 21 operations per second. And zetascale, is something which is many years out. It's not going to be, it's not something which is going to happen in a 3-year period of time. It's not something that's going to happen in a much longer, not 10-year period of time. It's going to happen in a much longer window. And some people are questioning whether or not we could actually afford or build such a system. And, I've heard those arguments in the past when we had petaflop computing. We can't possibly have a machine that runs at exascale. Was the claim, and today we have those machines. So I think, we will make it to those points. It'll take a while to get there. And I think we will have machines that are capable of those higher rates of execution, but it's going to take changes to the underlying architecture to get there. So new things will have to be created. I don't know what they are. Something will have to change at an engineering level to allow us to effectively get to those next large thresholds of performance. But I have faith in the fact that we'll be able to happen.
Okay, there are questions?
Thanks for your impressive talk. I'm a PhD student whose research is edge computing. I have a question. How do you foresee the integration of edge computing and high performance computing? Since edge device has a limited resource. For example, can large language model be trained on edge device in the future?
Edge is an important technology for use, and it requires computing power, of course, in order to process the data. We have stuff on, we have hardware that's on street poles that collecting data and sending them upstream to be processed. So small amount of computing on the light pole, and then as it's sent upstream, that information is processed and collected by higher computing power as it goes upstream and turned into something which is collected together with other sensors that are available and turned into something perhaps more meaningful by using the computing power upstream. So we're not going to have a supercomputer on the light pole. We're going to have a supercomputer someplace else, and we'll have staging of different kinds of computers that process the data as it comes off the light pole and goes upstream. And some data will be thrown away because it doesn't make sense, or because it's not part of the process, or we don't have to collect things every second. We can get by with collecting things at a larger frequency so that we can process the information. So decisions are made along the way where the data gets filtered, and the result of that is sent upstream and ultimately processed on a much faster, much more powerful computing system that is then used to drive any kind of decisions that are made. That story is we've done that before. We see it being done in sophisticated instruments. There's something called the square kilometer array. Square kilometer array is a radio telescope. It's an incredible device. There's two of them. One is in South Africa, another one is in Australia. And the radio telescope spans thousands of kilometers. And there's an integration of data that takes place to produce a uniform signal, as if the satellite, the radio dish was 1,000 kilometers large. Of course, it isn't. We've got devices that are collecting data, sampling it, down selecting, and then passing it upstream to computers, which then do the refinement and integration of that information to a signal, which represents something they're looking at in the night sky. So it's it's a similar kind of thing where the information is collected, they process it, filter it, and then send it to a place where the computation.
Okay, thanks very much.
We have a lot of questions, but we have only 5 minutes left.
Okay.
I want to ask this question. I think it's pretty interesting, talking about interdisciplinary research.
Yeah.
Okay. So, Professor Dongarra, I'm interested in about how interdisciplinary collaborations like at the University of Tennessee. And the question one, can you share with us if any specific developments at the Tennessee University to encourage different departments for interdisciplinary collaboration?
Right. So the University of Tennessee, it's a traditional school in many ways. There are departments, and those departments are silos where people are educated. And in some sense, it's unfortunate because there's not a lot of interaction between different departments. At the University of Tennessee, we set up an interdisciplinary graduate program in computational science. So the idea was that you can get a degree in your field and also get a degree in computational science, get a minor in computational science, by taking a number of courses in different disciplines and putting them together and doing a project, maybe working somewhere during the summer that is in line with the area that you're interested in. So the idea is to take courses not only in your department, but also in other departments, and have those selected courses, specific courses that are geared to this program, be counted in a degree program. So you would get a PhD or a master's degree with a minor in computational science. Your degree would be in whatever your domain science was, physics, chemistry, whatever the domain science was. But you would then have this specialization, which you could use perhaps to help acquire your next job. So that's what's done at the University of Tennessee. It's an it's a graduate minor program in computational science, which specifies courses in other departments that are eligible to be counted in this interdisciplinary program.
The same question B also interesting, asking for yourself personally. Here's your experience working with specialists in other fields. In computing projects such as Tennessee or deliverables are targeted for practical application like healthcare, urban planning.
Right, we're often, so it's important to be grounded in terms of real applications. So, I can't sit in my office and just think about algorithms for supercomputers without really knowing what the applications are. So it's important to get a handle on which applications are critical, which are the important applications, and then talk to the application scientists to see where they're having issues in terms of, in our case, the linear algebra or performance issues that they're having, and trying to resolve that in a way which makes their applications run better on these high performance machines. After all, they're not the specialist in terms of supercomputers, they're specialists in their area, and we have perhaps greater depth in terms of how to effectively use those machines. So, science today is really driven by interdisciplinary work. And it really needs a team of people to come together to effectively drive the science to push back those frontiers, and especially in computational area where, again, the domain scientists may not have the specifics to solve a problem on such machines. Getting together with application people, getting the algorithm people and the software people together in a room to hash those things out has been a core of very successful projects. There's a program in the Department of Energy called SIDAC, which does exactly this, does this interdisciplinary approach, trying to bring together teams of people to solve problems that pushes those domain science problems forward.
Maybe one more question from the audience here. Yes.
Hello, Professor. Thank you for your amazing talk. I am a fifth-year PhD. So, as you mentioned in your talk, I am quite curious about how to improve the computational efficiency when the input data is extremely sparse. And I'm wondering about the different perspectives to optimize this problem, such as the memorizing format or something. Thank you so much.
Right. So, sparse data. So if we're doing sparse operations, they often involve a lot of data movement, and operations have to be performed. It's going to depend specifically on the kind of problem you're going to be solving. In the case of these linear algebra problems that I was talking about, the data is a sparse representation of a matrix, and we have to manipulate that sparse information. And we try to do that in a way that aggregates the data together in terms of how the data is moved around. And you could think of another way of solving the problem, and we're working on parallel computing, on parallel computers. So some tricks that have been used. These are nothing really that's sophisticated, is replicating the data. So instead of having just the data in one place, replicate the data in a number of places on your parallel computer so that it's more accessible to the processor. So you're trading off storage in memory with accessibility, and the result of that is something that's going to run faster on your system. So it's going to, what you use to overcome these issues, if you can overcome them, are dependent on the nature of the sparsity that you have and the underlying algorithms that are going to be used to solve the problem. So it's hard to give a one answer solution to it. But there are some ways of overcoming some of these issues.
Okay, thank you so much.
I think one audience tried to for collaboration, saying that only you said last part you said only achieving 3% efficiency in the supercomputer. So he actually asked us what's the reason and what's the bottleneck.
Well, yeah, so we're getting only 3% on this sparse matrix problem. The underlying problem is data movement. So the data can't be moved to the processor fast enough. So again, we're measuring the efficiency based on the peak performance that the processors are capable of delivering. And the peak performance just says, forget about data movement. How fast can you do floating point operations? So that's the metric that we're up against, and we have to move the data, and that becomes very slow. And so think of it like this: it's taking 1,000 times what it takes to do a multiply to move the data to the point where the multiply is done. That's sort of what we're up against. So how can we improve that situation? We need to stage the data, perhaps. So we have cache that helps in that matter, but because of the sparsity and because of the method which iterates through the data, we don't often get the benefit of that cache. So we have to come up with other mechanisms that might help along the way. And some of that is to try to find blocks of data which are dense within the sparsity so that you can move the blocks and do more operations in that context. But it's all going to come down to communication is the thing which is limiting performance. And we have to find mechanisms to overcome that bottleneck.
Okay, thank you very much. I think we still have a long list of questions, but the time limits, so we will stop here. So let's thank Professor Dongarra again for the very informative and